This problem is actually pretty straightforward. We're just being asked for the largest ionization energy, and we're being given some information from which to choose. And so, really, when you're being asked something like this is clearly something that has to do with periodic trends. And so then we just have to think about the periodic table. I'll sketch that real quick. And what the trends that we've learned about the periodic table are. So, alright, so there's a periodic table, and we have the S, D, and P blocks. I've just separated them out so that it's a little bit more recognizable. And then we're thinking about ionization energy, and so hopefully we recall that ionization energy increases as we go from left to right and from the bottom to the top. And so really, we're just being asked to find the element that's closest to this upper right-hand corner. When we look at the answer choices in the periodic table, then we find the answer is phosphorus D, and then we're done with the problem. Again, it just comes down to remembering the periodic trends. Our next question is fairly similar. We want to know the most electronegative element, and then we're being given some information in the form of answer choices. Again, it comes down to remembering what our periodic trends are. So there's S, the D, and then the P blocks of our periodic table, and S, D, P, just to remind everyone. And so again, we want to know increasing electronegativity, and that again goes left to right and the bottom to the top. And so again, we're looking for something in the top right, and we have our answer choices to examine. And in this case, the one in the closest to the top right is going to be oxygen, and that's our answer choice, and that's the answer to that question. In the next problem, we're just being asked a series of questions, right, associated with 1, 2, and 3. We want to know which of these statements may be true, and then we're given some initial information, which is the electron configuration, the general electron configuration, right? And so you'll notice that when we look at this problem, we're given N for the principal quantum number. So we're concerned with any value of N, which means we're concerned with any of a particular column. And so here again, I would start by just drawing out the periodic table and thinking about what might have this particular electron configuration. Alternatively, you may look at this and realize that we're one electron away from having a closed shell, or being a noble gas. And so we just have to think about what elements need only one more electron in order to have a noble gas configuration, and these are the halogens. Right? But we can draw a periodic table like I just suggested, and so let's do that real quick as well. Right, so there's the D block, and then we'll have the P block here. Alright, and so if we think about the P block, right, we can see in this that the S orbitals are totally filled, and that the P orbital is just one shy. So that must mean we filled up both of these S block, S, D, and P, and then 1, 2, 3, 4, 5, 6. So this is the row that we're thinking of right here, which is one away from the noble gases, the end row here. And again, we find that this corresponds to the halogens. Alright, so then let's examine each one of these answer choices, assuming that we're talking about the halogens. Answer choice number 1 is saying that elements with this electron configuration are expected to form -1 anions. Well, we know that it's one away from being a noble gas, so that it would like to gain one more electron in order to be a noble gas. When it gains one more electron, that'll be a -1 anion. It probably won't gain any more electrons because it already has that noble gas configuration. And so I would say that's true. Number 2, elements with this electron configuration are expected to have large positive electron affinities. Again, when we think about electron affinities being large, we're talking about the element would like to gain another electron. And we know it really would, because gaining another electron would make it look like a noble gas. And so this also should be true. Again, we know that electron affinity as a periodic table or a periodic trend is going to increase left to right. So we'll call this increasing EA. And so left to right, basically by the time we get to the halogens, it really would like to have this electron added to it. And then finally, number 3, elements with this electron configuration are nonmetals. Number 3, that's just a simple, do you understand your periodic table? And we know that in the periodic table we have sort of this stepped row here where we have metalloids along the step, and then we have nonmetals on this side, and then metals on the other side. And then of course over here as well. Alright, so when we think about this row, yeah, generally this row is going to be on the nonmetal side, and so I would also call this true, and that leaves us with an answer choice of E, 1, 2, and 3 all being true. The next problem doesn't exactly ask us a question about a periodic trend, but it does touch upon sort of the central issue for periodic trends, which is the idea of effective nuclear charge. And in this case, we want to know what orbital, when we put an electron in an orbital, where is it going to have or experience the greatest effective nuclear charge for which of those orbitals? And we know that we're given a phosphorus atom, and then we're also given sort of some answer choices to choose from. When we think about effective nuclear charge, what I would think about is, in what orbital is the electron most likely to see the nucleus, or where it most effectively sees that nucleus? And so if I were going to think about what might give rise to that, is electron close to the nucleus, right? The farther away we are, then the worse we're going to see the nucleus. I think that just sort of makes sense. We know that electrons are farther away as our principal quantum number n increases. So if we wanted to be close to the nucleus, then we need to have a small principal quantum number. We can see right away that our smallest principal quantum number is answer choice A, so that seems to be the most likely, although this is not the only sort of consideration that we need to take into account. The other one is that the orbital needs to not have a node at the nucleus. Alright, so how do we think about what does not have a node? Well, we can think about the properties of orbitals that we've discussed. S orbitals satisfy this. And then P and D do not. So, if we want to have something, an electron in an orbital where it's going to feel the nuclear charge the most, we need it to be close to the nucleus, and we need it to be in an s orbital. We need a small n, and we need it to be in an s orbital. And again, A satisfies that criteria, And so A in this case is our correct answer choice. Okay, here, what are we being asked for? We want to know which of the following variations are correct for atomic radius. And then we're given some answer choices here to choose from. Alright, so this is a periodic trend. We're thinking about atomic radii. So let's just draw the periodic table real quick so we have something to refer to. There's the S, there's the D, here's the P block. S, D, P. And then we just think about atomic radii. What's the trend? Well, this is the one that's different basically than everywhere else. And so what we find is that the radius is going to increase in this case from right to left and top to bottom. That's because as we go through this trend, the effective nuclear charge decreases, and so the nucleus doesn't hold on to the electrons as tightly, and they're farther away from the nucleus. And so we'll call this our trend for increasing nuclei. Alright, and so now all we have to do is look at our answer choices and make sure that they move in this direction down the periodic table. So when we look at this boron and then carbon, that's incorrect. Carbon is to the right of boron, and so carbon is expected to actually be smaller than boron. So that one, we rule that out immediately. Sorry about jumping back to that last problem for a second. Okay, next. Nitrogen to phosphorus. Let's consider that real quick. Nitrogen is definitely above phosphorus for that, so that step works. And then phosphorus to arsenic. That also moves down the table. We essentially, for this, just go straight down for that choice. That's okay. That's a good answer. And then finally, fluorine, oxygen, sulfur. It makes this sort of like corner turn on the periodic table, but it goes right to left and then up to down. That is okay. That agrees with our trends. And so answer choice 3 is also expected to be correct. 2 and 3 are correct, which makes D our final right answer.